In this video, we're going to be graphing square root and cube root functions. Let's jump right in. The directions are telling us to graph the function, but first we want to identify the key characteristics. We can also talk transformations from the parent function as well. So the general form of any square root function, there is a number a that is multiplying by the square root of x minus h, and then we're adding some value k. And so let's start with the pieces of our function here. The a value is equal to 2, the h value is equal to 3, and the k value, that's equal to negative 4. So depending on how you look at starting these problems or how you build your patterns, I think it's a good idea to write down a, h, and k. But you always need to start by finding the domain. We do that by taking the radicand in this problem that is x minus 3. We set that greater than or equal to 0 and solve. So the reason we do that, if we choose a number in this problem that is less than 3, we're going to end up trying to evaluate the square root of a negative number. That result is imaginary. We can't graph that on the real axis. We want to stick with real numbers. So any number 3 or greater, we can substitute into this equation and get a y value out. It may be a decimal, but we can still get a y value out if we substitute a number greater than or equal to 3. The range, though, that's a little more straightforward, I guess. The a value is 2, and so that means that because a is greater than 0, this graph is going to be moving. It's going to be increasing as we move to the right. And so then our y values are going to be greater than or equal to the k value, negative 4. So range, that's the y values. They are greater than or equal to negative 4. And so if you wanted to write that as set notation, interval notation, we would say negative 4 to infinity. And the range we could write this way as well. We'd use a bracket because there's an equal to from 3 to infinity. All right, y-intercepts. In every function, if you want to find a y-intercept, you just evaluate 0. So I could try to substitute that in. We're going to run into an issue, though, because we're going to be evaluating the square root of negative 3. That result is imaginary. So in this case, because 0 is not in the domain of our function, there is no y-intercept. When we look for the x-intercept, what we're saying here then, we're substituting 0 for the y value. So we're going to have 0 is equal to 2 times the square root of x minus 3 minus 4. And so for this, we are just solving for x. We want to know the x value that produces a y value of 0. So we add the 4 to the other side of the equation. We divide by 2. 2 will equal the square root of x minus 3. And now we square. So to get this x out of the square root symbol, we're going to square both sides of the equation. It's going to give us 4 equaling x minus 3. And then we add 3, and we see that 7 is equal to x. So we do have an x-intercept at 7, 0. All right, let's talk transformations. If I tend to list the operations according to order of operations that are happening to x. So the very first thing we're looking at here, we would subtract 3 from x, and then we would do the square root. That's our function. I'm just going to put a dashed line right here. After that, we multiply by 2, and then we subtract 4. So everything above the dashed line is affecting x. So that's why this graph is moving right 3 units. Our h value is positive. Subtracting 3 means we are subtracting a positive 3. It moves the graph right 3 units. Multiplying by 2 is a vertical stretch by a factor of 2. So the graph is going to be twice as tall as it normally is. And then we're going to shift everything down 4 units. Okay, so this is the parent function over here on the graph. The point 0, 0 is where that graph normally starts. We're going to shift that right 3 units and then down 4. We know the point 7, 0 is on the graph. We determined that already. So all we're really going to do, we're just going to sketch this. This curve is going to do something like this and move in that direction. This is more of a curve and less of a line, but there we go. And that's really all you're trying to do. You want to be able to see the transformation that we shifted right 3 down 4. the graph is twice as tall as it used to be, and plot any points of interest. So that's the graph of f of x. Let's try one more. Let's talk through another problem. Down here, question number 2, we have g of x. G of x is equal to the negative 1/2 times the square root of x plus 2. In this problem, I'm going to switch to green. The a value is negative 1/2. The h value is 0. There is no number subtracted from x. And our k value is 2. So domain, once again, we set the radicand greater than or equal to 0. Couldn't get easier than that. Now, in this problem, our a value is less than 0. So that means our function is going to be decreasing, moving down. So f of x is less than or equal to 2. All right. Y-intercept, again, substitute 0 for x in any function, and you can find a y-intercept if it exists. So this would look like negative 1/2 times the square root of 0 plus 2. And in this case, f of 0 is going to equal 2. So we have a y-intercept of 0, 2. X-intercept, we set the y value equal to 0, and then we solve for x. Right? Negative 1/2 times the square root of x plus 2, we subtract 2. Divide both sides by negative 1/2, and you get 4 equals the square root of x. The only way to get rid of a square root is to square both sides of the equation. And so we're going to end up with 16 equals x. In other words, the point 16, 0 is on this graph. All right, transformations. Let's talk about the operations that are happening to x as they're happening. We would start off with the square root of x. That's the actual function. Everything after that is affecting the y. So there's a negative 1 that's being multiplied. I list this separately. We're also multiplying by 1/2, and we are adding 2. So the negative 1 that's multiplying is going to give us a reflection in the x-axis. The 1/2 gives us a vertical compression. So the graph is shorter than it used to be, and it's shorter by a factor of 1/2. The plus 2 at the end, that just moves every point up 2 units. All right, so let's plot our points. So the parent function has that point 0, 0. We're just moving that point straight up to 0, 2. Okay. We know that's the y-intercept. That's also where our graph, the domain begins. That's where our graph begins. So normally we would want more points to plot, but we can kind of we're just sketching this. We can use Desmos if we want to be really accurate. 16, 0 is somewhere way out here to the right. This curve is just doing something like this. It's going to go this way. So it's dropping down and it's moving to the right. All right, something like that, just a sketch. It's a good thing it doesn't have to be pretty. So one more function we're going to look at. This is the cube root function. We'll switch over to blue again here. So the domain and range are very easy for cube root functions. The domain and range always negative infinity to infinity. Another way to say this is all real numbers. That's a double stemmed R. Doesn't matter what transformations we do to the function. Always the domain and range for a cube root function are all real numbers. So we want to end up with a y-intercept. We substitute 0 for x. Negative 3 times the cube root of 0 minus 2 plus 1. Now, what you're thinking is probably what I'm thinking right now. I don't really know the square root of negative 2. Sorry, the cube root. So the cube root, though, we can use a calculator. It's going to give us some value, negative 1.26, I think, is what I wrote down here. My handwriting's not the greatest, but it looks like negative 1.26. We add 1. Multiplying this through, we're going to end up with a value of 4.78. So our y-intercept is 0, 4.78. Our x-intercept, this is maybe a little more straightforward. We're substituting 0 for the y value. We're going to have negative 3 times the cube root of x minus 2 plus 1. So we subtract 1. We're going to divide by 3. So 1/3 is equal to the cube root of x minus 2. We cube both sides to get rid of the cube root. So 3 to the third power is 27. That means 1/3 to the third power is 1 over 27. So 2 and 1/27 is equal to x. So that is our x-intercept. So 2 plus a little bit. I'm going to plot that point right now before I forget. That point is right here. 2 point, what was it? 2 and a small decimal, 1 over 27. The y-intercept was 0 and 4.78. That point's going to be up here. Now, we don't want that to show up. We want this here. Okay. So what I want to do, though, is look at this. We've got this point 0, 0. That's called a point of inflection. That's where this graph stops being concave up and starts being concave down. That's kind of outside our scope for this. But just notice it's where the graph changes, right? So when we think about what's going on this function, let's talk about our transformations. We say that we subtract 2, or we see that, and then we're going to cube root. So I'm going to put my dashed line here. Everything above is changing x. Everything below is changing y. We multiply by -1. Then we're multiplying by 3. Then I'm going to scroll just a little bit here, I think. Then we are adding 1. So we're going to shift this graph right 2 units. Then we're going to reflect it in the x-axis. That's what the -1, the negative does for the a value, the negative of the a value. The 3, that's a vertical stretch. It's going to be 3 times taller. All right, it's 3 times taller than the parent function. And then the +1 moves this up 1 unit. All right, so the only thing that's going to happen with this 0, 0 is that we're going to move it right 2 units and up 1 unit. So this point is here. So that is the point of inflection shifted from 0, 0 to this point. And so switching back to blue here. So normally this graph moves right 1 unit and up 1 unit. But we reflect it in the x-axis, and we're stretching this by a factor of 3. So it's going right 1 unit and down 3 units to get that height, left 1 unit and up 3 units to get that height. Oh, yep, I knew something seemed off there, but I'm seeing it now. I plotted my y-intercept in the wrong spot. The y-intercept is 4.78. I graphed it at 3.78. I had a little bit of concern for a second there. All right, so the curve's doing something like this. It's dropping down here, then it kind of flattens out. And then it's coming up through here, and then it kind of flattens out. So it's like a backwards letter S. And there it is. So again, these graphs don't have to be beautiful, but you want to be able to work through, finding the key characteristics, domain range. You want to make sure the transformations make sense, that you can list those, and then be able to picture the graph. It's either going to look like the letter S, or for square roots, it's going to look like, half of a graph because it's got this segment on it. So, take your time. If you need something that's a really exact graph, or it needs to be, really nice, use Desmos. But for our purposes, we want to be able to sketch and have an idea of what we're looking at.